Hi everyone, here in this video I would like to show you on how to find a moment on a statical indeterminate beam by using a moment distribution method. So first of all, let's say we have a problem like this. So here is our point A, point B, point C and point D, and the beam is fixed at point A and D, and we have here a pin connection at point B and C, and it's loaded by a concentrated load of 8 kilonewton, 1.5 meter from point A, and here uniform distributed load of 3 kilonewton meters, and here we have another concentrated load 16 kilonewton, which is 2 meter from point D. And for the member AB we have a moment inertia is I here, and for member BC we have a 1.5 I, and here we have I for moment inertia. So to solve for this problem, we have 3 steps here. The first one is to find the fixed end moment for each members. So here we will solve for the moment at member AB. So member AB, we analyze the member AB here, which is loaded by 8 kilonewton concentrated load. So moment AB is equals to negative 8 multiplied by the distance 1.5 meter here, and multiplied by the distance from this point up to here, it is 4 minus 1.5 meter. So we have 2.5 meters squared over the lever arm is 4 squared. So we have here the value of moment member AB is equals to negative 4.69 kilonewton meter. And the second one is the moment of member BA. We analyze this one. So we have here 8 multiplied by 1.5 meters squared multiplied by another 2.5 meter over 4 squared. So we have here we have positive value of 2.81 kilonewton meter. And the second one is to solve for a member BC. So we have member BC, we have here BC with moment inertia 1.5 I. So moment at member BC is equals to negative 3, which is a load, uniform distributed load of 3 kilonewton meter, multiplied by the lever arm 4 here, 4 square over 12. So here is equals to negative 4 kilonewton meter. And for moment at member CB, the positive 3 times 4 square over 12. So we have here positive value of 4 kilonewton meter, because we consider the clockwise direction is a negative value and counterclockwise direction is a positive value. So the next one is to solve for distribution factor for members meeting at each joint. So before solving for a distribution factor, we need to find the relative stiffness. So here the relative stiffness for member AB is equal to 0, because here at point A is fixed, and so there is no any distribution factor required for member AB. So member AB is equal relative stiffness also is equal to 0 because it's fixed end. And the second one is member BA. We have here moment inertia is here I, and the lever arm is 4, because for relative stiffness K is equals to moment of inertia over lever arm. So here 1 over I over 4, and for we have relative stiffness of member BC, we have 1.5 I, which is moment inertia here, over 4. So we can now solve for the distribution factor for member BA. Just simply equals to relative stiffness of BA over summation of relative stiffness BA and relative stiffness for BC. So we have here I over 4 over I over 4 plus 1.5 I over 4. We have distribution factor for memory BA is equals to 0.4. The next one is the distribution factor for member BC. Member BC. So here 1.5 I over 1.5 I, 1.5 I over 4 divided by 1.5 I over 4 plus I over 4. So we have here 0.64 distribution factor for member BC. And for relative stiffness for member CB we have here 1.5 I over 4. And then for CD, we have I over 3. Because here is, remember, moment inertia here is I, and the number arm is 3. So I over 3. Distribution factor for CD is the same here. I 1.5 I over 4 over 1.5 I over 4 plus I over 3. So we have here distribution factor of member CD is equal to 0.53. And the last one is I over 3 over I over 3 plus 1.5 I over 4. So you have here is equals to 0.47 for distribution factor of members CD. For DF, distribution factor of member D, there is no any distribution factor required here because here we have fixed N here, so it's equal to 0. So we are done with the fixed N moment and distribution factor for each member. So the third one is to make a tabulated form. So here we have the table here. I have the table with the values here. So first column we have joint member and distribution factor. Here is a fixed N moment and CO is a carryover. So we have here for joint A, we have AB because we have only one member, which is AB, because point A is a fixed N. For point B, we have member BA and BC, and for point C or joint C, we have member CD and CD. For joint D, we only have one member DC because joint D is a fixed N. So the distribution factor for member AB at point joint A is equal to 0, is equal to fixed N, and for BA is equal to 0.4 as we have computed here, and for BC is 0.6 and 0.53 for CD and 0.47 for CD, and DC is equal to 0 because it's fixed N. And for fixed N moment, we have calculated also here moment A, member AB, negative 4.69 kilonewton meter, and for member BA we have positive 2.81 kilonewton. Here we have negative 4 kilonewton and this negative 4 kilonewton, and here we have positive 4 kilonewton. And also I forgot to solve for this one, so we will solve for the this is member member CD. So for member CD, we have moment CD is equals to negative. Here we have 16 kilonewtons, 16 multiplied by we have the whole distance here is 3, so we have 2 here, so this one is equals to 1 meter here, so 1 square, 2 square over 3 square. So we have here is equals to negative 7.11 kilonewton meter. And for member DC, we have DC here. DC is equals to 16 times 1 square times 2 over 3 square here. So we have 3.56. Okay. Okay, here are the value for member CD and DC. We have the negative 7.11 kilonewton meter and positive 3.56 kilonewton meter. And the next one is a distributed moment. Distributed moment for AB is equal to 0, and for BA and BC joint A, joint B, there's two members BA and BC. So to solve for the distributed moment, we have to add these two multiplied by 0.4, we have this value of positive 0.48, and we add again this 2 multiplied by member BC 0.6, so we have here positive 0.71. When you have the value here is a negative, just simply manipulate it to be positive value, and when we have get the negative value, we just have to change it to negative value. Okay, so the next one is for joint C, we have member CD and CD. We have these two multiplied by 0.53, so we have positive 1.65, and this one is multiplied by 0.47, we have positive 1.46, and for DC we only have one member here, so this is equals to 0 because we have infinite value for fixed n. And for the carryover, at member AB, we just have to get the, because carryover can be by 4, because this one is a pin connection, this one is a fixed, so we can do the carryover. So we half of 0.48, we have here 0.24, this one is equal to 0 because we have here 0, and second for member DC and CB, half of 1.65 is equals to 0.82, and half of 0.71 is 0.36 here, and here we have 1.46, half of 1.46 equals to 0.73 here, so we have the carryover value here. The next one is for the distributed moment, second distributed moment. We have here is still 0 here, and here we have to add these two multiplied by 0.4, like what we have did here for this first distributed moment. So we add these two multiplied by 0.4, we have negative 0.33, and here we have negative 0.50, and this one we add these two multiplied by 0.53 and multiplied by 0.47, we have here 0.36, 0.36 here, sorry, this one 0.90, negative 0.90, and this one is negative 0.70. And for carryover, we just have to do the same thing as we have did here for first carryover. Half of 0.33 is equals to negative 0.16, and half of negative 0.19 is equals to negative 0.09, and half of negative 0.5 is equals to negative 0.25 here, and this one we have half of 0.17 here is equals to negative 0.08, and we just have to do the same thing as what we did in distributed moment, first distributed moment, and first carryover for the next third carryover, third distributed moment, and third carryover. And after we solve for carryover and distributed moment, we are going to finalize the moment. So we have here the summation or the final moment. Here at moment at A, or member AB, is equals to negative 4.59 km/meter, which is a clockwise direction. And here we have a positive 2.97 counterclockwise direction. And here we have negative 2.97. We have a moment for CD is positive 5.71, and for CD we have negative 5.71, and for DC we have, for fixed N we have D, we have positive 4.27. So here we can now put the direction of the moment here. For moment at point A, we have, or member AB, we have a negative value of 4.59. So this is the direction of the moment. It's clockwise. And we have the, for BA here we have positive, so this is counterclockwise. And for BC, we have clockwise direction. So this one is negative and positive. So the moment here will become equal to 0. The same thing done here, and for the fixed, and we have positive 4.37. So this is counterclockwise direction. Moment here will be counterclockwise direction. So we are down with the moment at fixed N and at the pin support B and C, which is 4.59 for fixed and A and 4.27 for fixed and D. So that's all. I think there should be any question or concern regarding the discussion. Please feel free to leave your comment. Thank you.